Hello, everyone. Uh, my name is Dave, Dave Eckroat, and I'm the director for IDEA StatiCa US. And I think we'll get started here. I know Mark has a lot of information to cover. And this webinar is now going to be on some of the verification studies we've been doing with the University of Tennessee to basically confirm that IDEA StatiCa is meeting the AISC requirements and kind of matching up with the code as far as correlation. So we've been working with several universities. University of Tennessee is one of them, University of Illinois, Chicago, as well as Ohio State University. Our plan is that kind of each one will do a webinar at some point, kind of break it up a little bit. But we're very excited to have Mark do the first one. Mark's been very busy with us for the last 2 years. So just to kind of give you a little bit of information about Mark. So Mark's an assistant professor in the Department of Civil and Environmental Engineering at the University of Tennessee, Knoxville. He's obtained his doctoral degree from the University of Illinois at Urbana-Champaign, and he has previously worked as a design engineer at Stanley D. Lindsay and Associates in Atlanta, Georgia. He's also an active member on several technical committees in AISCE as well as AISC. And then he is also a professional engineer in the state of Georgia. So with that, I'm going to turn it over to Mark. Thank you.
All right. Thank you, Dave, and welcome everybody. I'm really happy to be here to speak with you today. As Dave mentioned, I'll be discussing some verification studies that my team at the University of Tennessee, Knoxville, and I have conducted with IDEA StatiCa. Specifically, this presentation has 3 parts. The first is a brief introduction of the project and its goals. Then for the majority of the webinar, I'll highlight key results from studies as well as the process of the studies on specific connection types. Lastly, I want to summarize with some general lessons learned, as well as discuss the next steps in my research cooperation with IDEA StatiCa. So as you may be aware, IDEA StatiCa was born through partnerships with universities, primarily in Europe. So as they sought to expand in the United States, it was pretty natural for them to seek university partners in the United States. In 2020, they announced a call for research partners at universities in the United States, and as Dave mentioned, there was several folks that signed up for that, including my group at the University of Tennessee. And as Dave mentioned, I'm also the first one giving this giving you one of these webinars from one of the university cooperators, but I won't be the last. For each of these cooperations, the driving challenge behind the partnership is to verify, validate, and further improve the CBFEM approach. That's the approach used by IDEA StatiCa for steel connection design. And those terms, verify and validate, hold meaning. Unfortunately, they hold meaning to different people in different ways. And the definitions are not necessarily consistent all around, but there's some general trends in what they mean. So verification is generally the process of determining if a software was developed as intended. For example, are the finite elements working properly? And for IDEA StatiCa, generally the term verification is going to mean a comparison to an analytical method. Validation, on the other hand, is the process of determining if the results of the software meet the user's needs. Often this is a comparison to some sort of reality. And for IDEA StatiCa, that's often a comparison to an experiment. Now, for engineers in the United States, probably the most important and natural point of comparison for IDEA StatiCa is to the specification provisions in the AISC Specification for structural steel buildings. Now, this comparison doesn't exactly fit into either of the or lengthier definitions that I have on the screen here, but recognizing that the AISC specification doesn't always reflect reality, and following the IDEA StatiCa definition as well, we're really going to describe these comparisons as verification more than validation. And one thing I also want to point out in regard to verification and validation with IDEA StatiCa is there's definitely a recognition that perfection is unachievable. It's not intended to be 100% accurate. Really nothing, no model is 100% accurate in all cases. And then there's, but granted that there's going to be the recognition that there's going to be some errors in a direction. Really, the safe direction is the direction that the errors would hopefully be. And so identifying those was really a big part of the goal. So the project that I initiated sought to make comparisons between IDEA StatiCa and traditional calculations used in US practice for common connection types. Specifically, the goals were: 1, to verify that IDEA StatiCa provides code-compliant solutions; 2, to identify differences in results and the reasons for those differences; and then 3, to identify aspects of IDEA StatiCa that can be improved. When I started this project, I had not previously used IDEA StatiCa. I have had design experience with steel connections, so I really knew the importance of details and connection design. I had also run many nonlinear analyses through my research, so I knew how challenging those things can be. Because of these experiences, I really came to the project. My initial stance towards the software was skeptical but open-minded. And then based on that stance, really the things I was looking for, I wanted to shape the work based on what I thought I would want to see as an engineer before placing my trust in the software. You know, in formal terms, I've said to folks, I really saw my work as kicking the tires on this software, just to see and then document how it performed and how it did its job as a connection design software. When picking connections to investigate, I wanted to cover a wide range of aspects of behavior and controlling limit states. I was thinking to myself, you know, I wonder if IDEA StatiCa captures this effect or that effect, or how well it captures these things. And some of that is based on the experience with nonlinear analysis, thinking what would be hard to capture versus what would be easy to capture. And then I would think of a connection that would allow me to test that out. The first connection on this list here is T-stubs. And I'm not saying that this is the most common connection, but it does provide a nice clean comparison for prying action and the interaction strength of bolts. These clean comparisons are often the ones you can learn the most from. So I guess there's a mix here of common connection types and maybe less common ones, but simplified clean connection comparisons. And it might be better to have a picture view of the variety of connections that we investigated as opposed to the list. Also, when picking the connections to investigate, I sought cases where the traditional calculations were well defined. I drew much from the AISC design examples and design guides, and that's you know, these are cases where you know, IDEA StatiCa often shines in the cases where the design guidance is not well presented. But to make proper comparisons, I wanted to make sure I was comparing to things that had a lot of buy-in from the practice. And so looking into the AISC design examples and design guides provided a lot of good examples from which I could base those comparisons. Now, with an understanding of the project and how I approached it, I'm going to go through several of the studies highlighting key results as well as the process. The first connection is that one I just mentioned, a T-stub connection. This is the first one I want to highlight. And this one's explicitly based on an example from the AISC design examples. That example that I based this particular connection on was regarding combined tension and shear in a slip critical connection. And the first thing I really wanted to do was replicate the design example directly. As those of you who use the software know, you really have to define every little bit of the connection. You can't have undefined parts. So while the traditional hand calculations can proceed without a specific beam size or plate size or plate thickness, you don't need the information that you don't need specifically for the calculation. The IDEA StatiCa analyses can't proceed without that information. So I started from the design example and then added extra detail. So for instance, picked out a beam size, picked out some plates here, and also instead of that generic load, I welded an HSS to the stem of the stub plate to apply the loads. One thing I want to point out here is note that the dead load on this example is 15 kips and the live load is 45 kips. That results in a factor load of 90 kips. And so that was the first load that I applied in IDEA StatiCa. And applying that load of 90 kips to that HSS in IDEA StatiCa shows this result. Now that 90 kips of factored load was shown to be okay in the example, and the fact that it's not okay here, indicated by the fact that these bolts here are loaded up to 125.9% of their utilization. It indicates that IDEA StatiCa is conservative for this case, but so far we don't really know much else. We don't actually even know how conservative IDEA StatiCa is for this case based on these results alone. So the underlying analysis approach, the CBFEM approach, it's nonlinear, meaning that 125% utilization that we see on those bolts does not necessarily mean that the bolts, or does not necessarily mean that the load is 25.9% too high. We would have to kind of back out and maybe do some iteration to determine exactly how high we were. And that's really what we did, because these more informative apples to apples comparisons can be made by comparing maximum permitted applied loads. It's really just better to compare the maximum permitted applied load per the AISC specification, or the traditional calculations. If the AISC specification says that this amount of maximum applied, this is the most load that you can apply, we'll compare that to what the most load that IDEA StatiCa says that we can apply. And both of these are really determined in general iteratively. Sometimes you can calculate it directly in the traditional calculations, but the iterative approach was what we took in many cases. So for the AISC specification, or the traditional calculations, we can identify the maximum load, for example, by coding up the design equations in an Excel spreadsheet and then using goal-seek to identify the load that gets us right at the limit. In this case, the design example was pretty close. So instead of the 90 kips, 90.4 kips is the maximum applied load per the traditional calculations. In IDEA StatiCa, there is a feature called joint design resistance, which will give you approximation of what IDEA StatiCa would be the maximum applied load in IDEA StatiCa. But because there are some approximate aspects of that particular feature, what we did was a more precise trial and error approach to identify the maximum permitted applied loads. Really, we changed the applied loads up or down, and it would be down in this case, until we reached a point where a small increase in the applied load would switch the results from good to no good. And for this particular example, that was a load of 83.9 kips. And comparing that maximum permitted applied load of 83.9 kips for IDEA StatiCa to the maximum permitted applied load of 90.4 kips for the AISC specification, that indicates that IDEA StatiCa is about 7% conservative in this particular case. And note that that's not the 5.9% that you might have initially guessed based on the bolt utilization. Now, this is good information that shows that IDEA StatiCa is conservative, and by how much. And IDEA StatiCa strives to be accurate or conservative, but it doesn't really speak to why the differences exist. So you got to dig deeper for that. The checking results provide some clues. And so here's a screenshot of the calculations for one of the bolts in the connection. The equations are all implemented correctly, but in the calculation, one factor, this KSC factor, that's the factor for combined tension and shear, it's slip strength reduction, really. It's different than what was calculated in the example. And it's also clear what the reason for that difference is. It's the required tension force that goes into that equation is different between IDEA StatiCa and what we see in the design example. While you can follow the calculations in the design example and they make sense, to determine this FT, the required tension force in the calculation. This value in IDEA Statica comes from the analysis, so there's really no calculations to review. And now here's where a solid background in the behavior of steel structures helps. You got to think to yourself, why could tension in these bolts be different than expected from the applied loads? And going back and thinking about this T-Stub connection, to me, the obvious candidate is prying action. And so I went forward with that as my reasonable hypothesis. To test this hypothesis, I did a few things. So for instance, the first thing I did was say, hey, let me take a look at the contact pressures. So I used the stress and contacts option, and I did see, hey, look, at the tips of the flanges of the T, we are seeing contact pressure. So that's kind of implying that there is some prying action going on in this particular connection. We can further investigate this by varying the flange thickness. If the hypothesis of the difference having something to do with prying is correct, then the difference should disappear as the thickness of the plate increases and the prying action disappears. And so we have this set of results, which is those applied loads, maximum permitted applied loads for IDEA Statica and the traditional calculations as a function of T-stub flange thickness. And so I believe it was the 1-inch flange thickness that I had in the previous example. So you can see about this 83 Gips versus the 90. You can see that for the traditional calculations, there's really no variation with T-stub flange thickness, but for IDEA Statica, there is some variation with T-stub flange thickness. So after running several analyses with the same connection but different T-stub thicknesses, we see that with increased thickness, the prying action decreases eventually to 0, and that the results converge to those from the design example. So with the thicker T-stub flange thickness, this 1.5-inch plate, we're matching up precisely with the traditional calculations with IDEA Statica. So this is pretty good evidence that the difference does have something to do with prying. But we still don't know why there is a difference. So you could review IDEA Statica's literature on how things are modeled under the hood. Question to support might be helpful if you're not sure. It was, for me, figuring it out through conversations with staff at IDEA Statica that to figure out the reason is because the bolts only really know what is subjected to them and cannot distinguish between tension due to applied loads and tension due to prying action. Furthermore, those contact surfaces, that contact pressure in IDEA Statica, it's modeled as frictionless. So both of these explain the reason why we're seeing this reduction in strength for IDEA Statica. And both of these really seem like reasonable and conservative limitations of the program. And they really fully explain our observation. So this is one case of kind of going through basically a scientific exploration of what are the differences. You come up with a hypothesis, you test that hypothesis. And I'd say that this process certainly left me with a better understanding of what IDEA Statica can do and cannot do. It's certainly that this process was much more helpful to me than any amount of just sort of study without actually running these experiments would produce. I would say it also has left me with a kind of a, it helps deepen my understanding of steel structures. And I would say all of these things would leave anybody who executes them with this deeper understanding of IDEA Statica as well as the behavior of steel structures. Really, and this knowledge is gained through this process, I would say, is helpful beyond this specific example. The specific example is actually somewhat contrived. Prying action, contact stresses, slip critical bolts subjected to tension, they're really, these are seen in other connections as well. And going through this process really helps me have a better understanding of what's going on physically and what's going on inside the analysis software. And part of communicating these results to you in this webinar and in the web articles that we've written is meant to help you understand these things better as well, and really help inform your judgment as you design connections. Moving on from the slip limit state, the T-stub is also good for evaluating flexural yielding of the plate, tensile bolt strength, and how these two limit states are coupled by prying action. For these comparisons, we changed the angle to 90 degrees, perpendicular to the beam, and the comparisons were made to the method for capturing prying action in Part 9 of the AISC manual. Now, when doing this work, I was always conscious to understand what parts of the traditional calculations are mandatory and which parts are not mandatory. So when the method of Part 9 of the steel manual for dealing with prying action is not in the specification, and thus it's not a mandatory method. Other methods, including the explicit modeling of the connecting elements in IDEA StatiCa, they're okay to use per the specification. Note, however, that the tensile strength of a bolt that is governed in the specification, and that's not something I would say that's a mandatory part of connection design, and IDEA StatiCa relies on those equations in the specification to calculate the bolt utilizations. Yielding is a different sort of case of a thing. So flexural yielding of the T-stub flange or the beam flange. There are mandatory equations in the specification, and IDEA StatiCa essentially captures those more in the spirit of the specification rather than the letter of the specification. There are no, M equals, FYS in calculations going on behind the scenes in IDEA StatiCa. It's really the fact that IDEA StatiCa captures the yielding as part of the material nonlinear analysis and further applies a plastic strain limit of 5%. But as we do these, compute these results, and here what we see is, again, results with variability between variability of the T-stub flange thickness and showing the maximum permitted applied loads for both IDEA StatiCa and the traditional calculations. We see a lot of the same general behaviors. We see for both methods, the traditional calculations and IDEA StatiCa, the three regions of behavior that typify prying action. For the thickest plates, where only tensile strength of the bolts controls, so in this region up here, there's no difference between IDEA StatiCa and the traditional calculations, and this is expected because there's no prying action in this region, and the AISC IDEA StatiCa implements the specification equations directly. For the intermediate plate thicknesses, in this region here, where bolt tension and flexural yielding control simultaneously, IDEA StatiCa is conservative. The maximum load that IDEA StatiCa says can be applied is less than that for the AISC specification. One reason for this is the fact that the recommendations in Part 9 of the AISC manual utilize FU instead of FY for the bending strength. What we can do to test that out is really run another set of calculations where FY is used instead of FU in the traditional calculation, so a variation on what is presented in Part 9 of the AISC manual. And this brings the results closer to IDEA StatiCa for the intermediate plate thickness range. Now, the third region of behavior over here is for the thinnest plates where flexural yielding controls. The tensile demands in the bolts are increased because of prying action, but they don't reach their capacity. So it's really just the flexural yielding is controlling here. And here, IDEA StatiCa is showing a greater permitted applied loads than the traditional calculations. Now, these cases might not be the most practical because a 1/4 inch thick plate probably would just not look right and not be used by most engineers. But since they are on the unsafe side, these, in comparison to the traditional calculations, they warrant a closer look. And this particular case has been investigated before. So similar observations were observed in previous comparisons to European standards. So this study, results from this study, which I'm showing on the slide right now, were published in IDEA StatiCa's verification book, which also compared the European standard to the results of IDEA StatiCa, and had a further comparison to a more sophisticated finite element, sort of a research-based finite element model. And what this study found was that the strength from the research-based model was greater than either the IDEA StatiCa, the CB-FEM results, or the code-based approaches. So these results are really suggesting that the traditional calculation methods underpredict the true strength. And despite IDEA StatiCa giving higher strength than the traditional calculations, that IDEA StatiCa would still be conservative. Another thing that we investigated occasionally, and really whenever I thought that it might matter, was mesh refinement. So IDEA StatiCa has made a choice on the default mesh size that balances accuracy and speed, but you do have the option as a user to vary the mesh to determine if your problem is sensitive to mesh density and by how much. So like before, these are maximum permitted applied loads from the traditional calculations, and then 3 versions of IDEA StatiCa, one with the default mesh size and one where the mesh size has been decreased to 2 smaller levels of mesh. And so we see in this case that there is some sensitivity of the results to the mesh density, especially when prying action controls. In this region up here, where with the bolts control, as expected, we're really not seeing any difference. But over in these regions, we are seeing some reduction in strength, according to IDEA StatiCa, as the mesh gets refinement. This gets a little bit tricky because given the way that IDEA StatiCa models bolts, welds, and connected plates, a finer mesh does not always produce a more correct answer, but it does provide some useful information to look at this every now and again for particular cases. In addition to bending of the T-Stub flange, we have bending of the beam flange. So in this case, the yielding pattern is more complicated. I show it up in the upper right-hand corner. The traditional calculations here are starting to get more complicated. We're approaching the limits of thoroughly validated and widely accepted design guidance. Now, obviously, things get much more complicated from here. And I guess one of the main advantages of IDEA StatiCa is that we're really nowhere near the capabilities of what can be modeled in IDEA StatiCa, even if we're at getting towards the limits of what there's really thoroughly vetted design guidance for. These results show that that when looking at the beam flange bending, we see some good comparisons between IDEA StatiCa and the traditional calculations, especially the version of the traditional calculations where we have Fy instead of Fu governing the yielding strength. The next connection type that I would like to talk about are bracket plate connections. Unlike the T-stubs, these are not terribly common connections, but they do allow for a relatively clean evaluation of eccentrically loaded bolt groups. For the traditional calculations, the strength of a bolt group is determined using the instantaneous center of rotation method described in Part 7 of the AISC manual. And an interesting thing happens in IDEA StatiCa for these connections. The bolt utilization percentage does not increase linearly with applied load. The relationship which I show here between applied load and bolt utilization it's kind of a somewhat strange, starting with a linear increase followed by a plateau and then followed by another linear increase. The plateau occurs right at about 100% utilization, and it's most of the way through the plateau that IDEA StatiCa indicates with a red X that the connection is overstressed. Note that the load at which IDEA StatiCa says fails the member is actually pretty darn close to where it, the strength from the traditional calculations. Now, the cause of this plateau is related to the constitutive relation for which is applied to the nonlinear springs representing the bolts, and the fact that you can redistribute force upon yield. But what I take away from this result, and it's kind of a little bit surprising as I was flipping around the numbers and seeing these results, is that the bolt utilization percentage really can tell you which side of acceptability you're on, but not really how far from the limit you are. So at 130 kips of applied load, you might have something really darn close to 100% utilization, but you still have quite a bit of extra strength here. You can do applied loads up to 170 before you're at the limit. The reverse is possible too. So in hand calculations, you might accept a 2% stress every once in a while, knowing that the calculations you just ran mean that a 2% less load would be okay. But 102% utilization, something over here, may come from loads that are 10% greater than those that the program indicates cause failure. So really, engineers should really still be exercising their best judgment, regardless of the tools they use. But the best judgment comes from informed engineers. So knowing the behavior and knowing what your tools do and don't do. If we take a look at the strength results, and so again, relying on where IDEA StatiCa goes from the to the red X, the load that gets us, trips us right over that limit, IDEA StatiCa matches really quite well with the traditional calculations over a range of eccentricities. We tried other bolt groups too with similarly good results. Moving on to what is actually a very common connection, the single plate shear connections. I have them next here because they include eccentrically loaded bolt groups, as well as a variety of other features that make for some interesting comparisons. As many of you may know, Part 10 of the AISC Manual describes methods for design of this type of connection, and there's really two methods, one for a conventional connection and one for an extended version of the connection. The conventional connections are those that have a single vertical row of bolts. The distance between the bolt line and the weld line is less than or equal to 3.5 inches, as well as satisfying other limits on edge distance and plate thickness. An important part of the design of these connections, albeit whether it's IDEA StatiCa or the traditional calculations, is selection of the point of zero moment. A common assumption is to have the point of zero moment located at the weld line. And this is what's baked into the traditional calculations defined in Part 10 of the AISC manual. They utilize this assumption. However, I'll note that for the conventional connections, the method does permit using half the distance between the bolt line and the weld line as the eccentricity for the bolt group. In IDEA StatiCa, you're explicitly defining the point of zero moment as part of the definition of the model. It's an input to the model, and it's a thing that you're going to be setting as an engineer. For the cases shown, the strength of the eccentrically loaded bolt group controls, and the comparison is quite good. But we might have expected that since we found in the previous study that IDEA StatiCa matches the instantaneous center of rotation method quite well when examining bracket plate connections. There is a difference between IDEA StatiCa and the traditional calculations for these conventional connections, with the conventional coming in at a higher strength than what IDEA StatiCa predicts. But that's the result of the ad hoc rule permitting a lower eccentricity to be used in these conventional configurations. If you might get some similar results in IDEA StatiCa if you adjusted the point of zero moment to be more consistent with that assumption. We can investigate smaller edge distances with these particular connections, these single plate shear connections. Tearout can control the strength of some bolts in the bolt group, and this is a tricky thing to handle in the traditional calculations. The most common approach is to use the poison bolt method. Essentially, since you're not sure which bolt will be controlled by tear-out and which ones won't, and because the tables in the manual do not allow for groups of bolts to have different strengths among the bolts. Really what you do is you assume the worst case bolt strength and you use it for all the bolts. And this poison bolt method, as described, is quite conservative. And as we go for different plate thicknesses and pretty small edge distances for that single plate shear connection, what we see is a reduction in strength when using the extended method and the poison bolt method. And we see higher strengths being provided by IDEA StatiCa. And these higher strengths, I would say, make a good bit of sense because in IDEA StatiCa, the tear out is based on the direction of force determined from the analysis, and it's evaluated on a per bolt basis. Using this direction of force allows for higher strengths if the direction is not the worst case. So as shown here, it's this bottom bolt here, number 3, where the tear out would primarily be controlling. And the direction of force is towards more the corner, where there's more clear distance than if the direction of force was straight down, as would be assumed in the poison bolt method. It's important to recognize that, this poison bolt method, and in fact, all the stuff in the all the extra stuff defined in the manual is not mandatory, like the specification provisions are. And so, having this difference, although it provides a higher strength in IDEA StatiCa than maybe the traditional methods with the simplified guidance, there's really good reasons for these differences. Next, I'll talk about extended in-plate moment connections. I wanted to investigate these connections because I knew that the traditional calculations had some particularly heavy equations based on yield line theory as part of the method. And like the other connections, the main results were, varying some parameter, typically, as the case here, a thickness, and specifically the end plate thickness, and identifying the maximum permitted applied loads, maximum permitted moment here for both IDEA StatiCa and the traditional calculations. And I think there's a lot of interesting observations that can be made from this plot. For one, IDEA StatiCa does capture reductions in strength when the plate gets thin and flexural yielding of the end plate starts to control. The traditional calculations don't. And they don't because there's really not guidance necessarily for these thinner plates. There's not guidance for these thinner plates because prying action can start to occur, and the guidance is that you just make your plate thick enough that prying action will not occur. When you think about these thinner plates, you should probably also be worried about the connection no longer being rigid. If the plate gets too thin, it might become more flexible and not act like a fully restrained moment connection. So this is actually kind of an extra thing that could be evaluated with IDEA StatiCa. And I've indicated that with the different markers here for the different plate thicknesses. Anything with this empty square marker was indicated as a rigid connection by IDEA StatiCa, and everything else was indicated as a semi-rigid connection. And the limitation on plate thickness where that occurs, the boundary between rigid and semi-rigid, is basically the same as what you'd expect from the traditional calculations. As the plate becomes thick, so the other end of the graph, what you see is that tensile strength of the bolts controls the strength. And you start to see IDEA StatiCa having higher strengths than the traditional calculations. And upon investigation, really the reason for this is that the lever arm for the couple formed between the tension in the bolts and the contact pressure, it's an assumed value for the traditional calculations, and it's a calculated value from the analysis. It's not explicitly calculated, but it comes naturally from the analysis in IDEA StatiCa. And as the plate gets thicker and stiffer, it has more of a capability to have higher contact pressures out at the farther end, and really it extends out that lever arm, increasing the strength of the connection. And we can see that for looking at a couple different cases, with one with a thinner plate where the contact pressure is centered a bit more closer to the flange Note that in the traditional calculations, the contact pressure is assumed to be centered at the centroid of the flange. But as we get to thicker plates, comparing 7/8 to a 2.5 inch thick plate, you can see the contact pressure being the highest right at the tip of the flange. It's a stiffer plate, stiffer and stronger plate that can accommodate those higher stresses out at the far end. So the lever arm between the bolts and the contact pressure is just increased here with respect to the thinner plate, and certainly with respect to the traditional calculations. Another example where we're seeing higher strengths from IDEA StatiCa, but for what I would argue are very good reasons. The extended in-plate moment connections are also good for evaluating panel zone shear. So the provisions of AISC Specification Chapter J provide two equations for panel zone shear. One for when the panel zone inelasticity is considered in the frame model to determine required strengths, and one where it's not. If you consider the extra deformations that occur from partial yielding of the panel zone in your frame model when determining required strengths, you actually get more panel zone shear strength to work with. In IDEA StatiCa, using the default plastic strain limit, the resulting strength is really more comparable to that higher of the two strengths. This is something that's probably pretty good to keep in the back of your mind, since I believe it's not terribly common for frame level models to consider the plastic zone inelasticity. Now, if you were concerned about this and really would prefer to have the smaller of the two strengths, one thing that you could do is change the plastic strain limit to something quite small. Here I changed it really to 0.1%, which might be a little bit overkill. 1% might do good. And what you see when we change the plastic strain limit, don't allow as much yielding to occur. We see that the results are comparable to the lower strength in the AISC Specification Chapter J. But really, that's something that that you as an engineer would need to know as an aspect of your as sort of a feat and as an aspect of the program, the tool that you're using for connection design. The last collection I will discuss, and it's going to be relatively brief, is one without well-defined traditional calculations. This is a temporary erection splice that makes use of these four mule ears, as they might be called. The purpose of investigating this connection wasn't the same as the others. It was really to evaluate the process of coming to trust the results and to maybe demonstrate that process as well. As well as, the process of getting the results necessary to make informed decisions in design. This connection is not a standard form, and it also doesn't have standard loading. It's got actually some pretty complicated loading. It's got axial compression, shears in two different directions, bending moments in two different directions, as well as some twist. With this non-standard connection and non-standard loading, simply looking at the final results doesn't give you a great understanding of its behavior. If it's hard to tell if you're in a garbage in, garbage out situation if you don't know necessarily what you expect. So the general approach that I took was to look at each action individually and make sense of them. Looking at the axial compression alone, I was able to do some comparisons to how I might do that with hand calculations and gain trust in the model. Looking at the shear in the different directions, I could do the same thing. And so what I liked about this particular study was it kind of mimicked what engineers might do when they come across new and unique connections. As you can see here, the deflected shapes are particularly helpful for identifying truly what's happening in the behavior of these connections. And I would say understanding the behavior of the connections is one of the things you definitely want to do when you got a critical and unique connection. So to summarize all of what I've been talking about, really, IDEA StatiCa and the underlying CB-FEM method, they really form a rational method of connection design. And while not a replacement for engineering judgment, really safe designs should be expected for properly defined models using the default analysis and design parameters. Care is going to be required when defining the model to ensure that the behavior of the connection is as intended. And there's some other conclusions as well in terms of like some common sources of where conservatism in IDEA Statica comes from, as well as some common sources of where IDEA Statica gives greater strengths than the traditional calculations. But one thing that I personally would particularly like to emphasize is, I started, like I said at the start of this webinar, that I came to this project skeptical but open-minded. Conducting this research has made me far less skeptical. I have sort of my baseline level of skepticism on for software when using IDEA Statica, which often is related to, did I model the thing correctly? I really think IDEA Statica is a powerful tool that has a place in structural engineering design practice. And really, furthermore, as you want to develop your knowledge and your confidence in the program, I really think executing studies similar to those that I've shown today is one of the best methods to be doing that. It's a good method to help you better understand the software and gain further confidence in the results. So my research cooperation with IDEA Statica between my research group and at the University of Tennessee and IDEA Statica, it's ongoing. So current and future work includes a thorough evaluation of the limit state of tensile rupture with comparisons to experiments and reliability analyses, as well as developing sort of a catalog of limit states, behavioral effects, and common connection components with a description describing how each of these is captured in IDEA Statica. It's another thing I actually quite like about IDEA Statica is they're investing in this in validation studies by myself and the other university partners, and it's really actively being developed. I've seen improvements to the software from some of my studies, which is actually a very nice thing to see. I think it's a good thing that we have that it's a actively developed software that is trying to improve over time. So before we get to the questions, last thing I'd like to do is acknowledge my former master student, Kayla Truman-Jarrell, who conducted the work with me. I'd also like to thank IDEA Statica for funding the research, and specifically Dr. Martin Weld for his guidance and assistance. And with that, I believe we have some time for questions.
Thanks, Mark. We really appreciate you doing this for us and helping kind of show how IDEA Statica can be used for designs here in the U.S. So we are getting starting to get a couple questions. If anyone has any questions, please feel free to put them in the question module or item there. Let's see. The one question that we have is great webinar. I wanted to ask if you did an evaluation or verification about base plate connection for steel columns bearing over concrete columns. And it looks like there's a couple of questions about base plates. Mark, you haven't done anything with base plates, and I'm just trying to think off the top of my head.
Actually, I did.
Oh, okay.
I had noted it on one of the slides on the list of connections was base plates. That's a forthcoming article. So what you saw in this presentation, you find on the IDEA Statica website. Probably the easiest thing to do if you're looking for specifically this stuff is search Tennessee in the IDEA Statica website, and these are particular articles as well as this webinar will pop up. But baseplate connections is a study, and I would say that one's forthcoming, and it'll be on the website when it's ready.
Sure. Okay. Let's see. There was another question about performing tests on composite beams, so concrete slab and steel beam splices in IDEA. I don't know that we've done any verification on that, but since we've added the lateral torsional restraint into the software, it definitely has, it basically mimics that concrete slab, that composite action within it. I don't know that we've done any studies specifically about that, since it is a we've only had that restraint in there for about 6 months at this point.
Yes, I'm not aware of studies that I've
Right.
conducted or otherwise of
Yeah.
that connection.
Let's see. I guess, and Mark, and I don't know if you've run into it at all during your studies, but kind of any opinion, or have you done anything on slotted holes or oversized holes in any of the studies so far?
Uh, it that is something that I know I've looked at, and I don't recall if it's ever gone into one of the published web articles, but I do recall it, looking at it.
Hmm.
Um, uh, but I don't I don't recall
Yeah,
exactly what the conclusions of it was.
sure, sure. No, and that's something we can kind of pull together and
Yep.
send back out to, either put it into a separate article with working with Andrea, or because I think that's something that we get the question quite a bit. Let's see. We have another question here. It's how to set the zero moment point as set at single plate connection. So that's really within the software. When you select a model type, kind of on the member, you can adjust where the load is being applied, and basically where you're applying that load will set the zero moment point. Um, so if you can kind of adjust that right within the software itself.
There's also a nice feature to check that you make sure you did that right. I think you have to turn on maybe the wireframe, and
Right.
you can see the moment diagram on the members.
Exactly. Exactly. Um, do we have any other questions? We'll give it another minute. I think, Mark, you just did too good of a job explaining the verifications that you've worked on.
Well, I strive to do that. Uh, I'll,
Uh,
I switched it over to the thank you slide, so it will. I did
okay.
a good job.
Yeah. I mean, if anyone has any other questions, just feel free to reach out to us. Um, yeah, the general email for IDEA US is office@ideastatica.com, or reach out to any of our team here. Once again, Mark, appreciate you taking the time to put this webinar together and kind of show some of the work that you've been doing. And we'll definitely have to, once we get through a couple of more phases, we'll do another one.
Great. I look forward to it.
All right. Thank you. Let's see. Okay, we had one quick question, one last question come in at the last minute. For the T-Stub Flange connection, did you limit the plastic strain to 5%?
Yes, that's the default, and so we had some. That's what we were showing. I have in perhaps not in the T-Stub, but in other verifications, varied that plastic strain limit, because I think it does show some interesting results as you vary it.
Okay. All right. Well, with that, we're going to actually shut down the webinar. Again, if you are interested in rewatching it or want to kind of review it again, we will be posting it to the website, at idea.com, at ideastatica.com, as well as our YouTube channel. So with that, again, Mark, appreciate it. And everyone have a good day.